Hi, welcome back to this course on differentiable manifolds. If you can look at the whiteboard before, you can still see rest from the last class. If you have a look here, let's have a look. We can still see very barely the properties, the exercise 11, in which we were solving, we were checking that the bracket associated, the Poisson bracket associated to a symplectic structure is really satisfies the conditions of Poisson, which were anti-symmetry, Leibniz rule, and the one which was harder to prove, which is not on the side of the blackboard, is the one of Jacobi identity. And today we're going to explore this new world of Poisson geometry. But as a first motivation for the importance of the brackets, I will talk about integrable systems. Okay, so in this first video, the idea is the following. The idea is that we start, like, remember one thing we mentioned in the last class is that this equation here that you can see, you can read, which is anti-symmetry, we could interpret this as Noether's theorem. Okay, Noether's theorems in the sense that the trajectories of a vector field, were contained on h equal to constant. Therefore, if we interpret the h, the function h, as the total energy of the system, this is equivalent to conservation of energy. So we were able to prove Noether's theorem just because our bracket was anti-symmetric. This is like quite interesting. Okay, so today what we're going to do is we're going to a little bit study the relation between integrability of a differential equation and Noether's principle. Okay, Noether's principle is telling me that if I have a Hamiltonian vector field, I know that the trajectory or the solution, if you want, to the differential equation associated to this Hamiltonian vector field, it's going to happen on h equal to constant. This means that if my symplectic manifold has dimension 2n, then the trajectory of this particle is going to move on h equal to constant, which is an hypersurface with, as you know, in a generic sense, I can think that this is a submanifold of dimension 2n minus 1. Okay, so this reduces by 1 the degrees of freedom. Okay, in principle, it reduces by 1. But something very interesting happens when you have symplectic geometry. Because of this game of the duals, whenever you have one elimination of variable, automatically you multiply it by 2. In that sense, if you want to solve an integrable system and you want to solve it explicitly, it was an idea probably back to Jacobi or Liouville. Jacobi, Liouville, let me think. Well, I'll try to post a video up there now where this is explained. In order to solve the differential equation of a Hamiltonian vector field, it's enough if you are a manifold of dimension 2n, because this is symplectic, because you can think that this is locally like a cotangent bundle of a manifold, therefore always even dimensional. Okay, then this idea of Jacobi is it's enough to have n first integrals of this vector. But not any n first integrals. It's going to be enough to produce the magic of solving the differential equation. These functions have an additional constraint. They need to Poisson commute. It means that if I compute the Poisson bracket of 2 of them, which I can simply compute, and I can look back here up there in my whiteboard that you can, let me see. You can now see perfectly, okay, because I have a judge, so you can see this. Now, if you look at this equation up there, okay, this equation up here defines the Poisson bracket in terms of the symplectic form, okay, and it's a symplectic form of the Hamiltonian vector fields. Therefore, it's a computation to check whether or not two functions Poisson commute. What is more difficult is to find this, what we call first integrals. All this language is a little bit inherited from the theory of differential equations, but also from physics, okay? So what is not so like physically, it's sort of hard to find these first integrals. Indeed, not always you can find such first integrals. Indeed, if I have a box of Hamiltonian systems, again, I can take my imaginary box and I put my hand inside the box, then the set of vector fields, the set of vector fields, Hamiltonian vector fields, which are integrable, is going to have zero measure. Why is that? If you look at the equations that the Poisson bracket equals 0, and you think of our first chapter of this course on Introduction to Differential Topology, this has to be a set because of Sartre's theorem. This has to be a set of measure 0. So inside the set of Hamiltonian vector fields, very crazy things can happen. And I can say that integrable systems, from a point of view, it's like not a sheer representative, not a really honest representative of what is going on in the Hamiltonian business. But it's a very good first approach where we can put our hands on. Very interesting thing happens for an integrable system. The first is this motivation coming from, I want to integrate these differential equations, and an integrable system allows to do this by quadratures. This is exactly the way that Jacobi presented integrable systems, so that you can integrate your differential equation by quadratures. But not only that, well, you can play with these first integrals and interpret each elimination like what is called a symplectic reduction. So you can read that from symplectic geometry. Well, what is the most important theorem concerning integrable systems? The most important theorem is a theorem classically known as Arnold-Liouville theorem, but today we're going to discover the truth. Stay tuned. Which tells me that this Darboux form that I have in a neighborhood of a point that we proved in a couple of videos ago, here in this video, okay, we proved Darboux theorem. But now Darboux theorem tells me that things are locally the same in a neighborhood of a point. What Arnold-Liouville theorem is going to tell me is that everything looks the same in a neighborhood of a fiber of the integrable system. How interesting is that? Well, you need to have some conditions of the fiber. Nothing comes for free. And the condition that it's quite natural to impose, at least as the geometers and topologists, is that this fiber is compact. Indeed, it's enough to assume that this fiber is complete to have a kind of Darboux type theorem. Okay, if this fiber is compact, then automatically you can prove that in a neighborhood of this fiber, and if you take all the first components of your integrable system and equal to a constant, and you vary this constant, then what you see is a fibration by tori. These tori are called Liouville tori. Indeed, it was not Liouville who proved that the motion was going to happen on a tori, but he proved the existence of an invariance manifold where the trajectory was going to move. But he didn't assume that it was compact, and he didn't prove that it was a torus, but it's usually called Liouville torus. And then you have a fibration by Liouville torus, and you know what? What you're going to find striking is that the symplectic form in the neighborhood of this torus is a Darboux form. And you can do this in some important coordinates, which are called action angle coordinates, because they have a sense, it has a sense that things move on this torus, and action, that's an interesting point. This has to do with momentum. So if you're interested in what I'm explaining now, stay tuned. Now what I'm going to show in these first videos is some slides, and then in the next video, I will use my iPad. I hope you like this video. See you later. So now what I'm going to do is I'm going to share with you, okay, I need to share with you this video, these slides, okay. Okay, so, okay, in this first slide, what I'm going to do is to put full screen. Okay, great. So in this first, now I can move because this is like I decided I could have taken you to my magic library. Maybe I will do this in the next video instead of this, but I wanted to show, you know, my whiteboard because I'm very proud of my whiteboard. What can I say? Even if I'm the only one who's proud of my whiteboard. Okay, so let me talk about Noether's principle again. Noether's principle, so in this first picture, this is the simple pendulum. So remember the video of Joachim here, where he was dealing with a pendulum moving on space, and this was called the spherical pendulum. So this is the simple pendulum. You assume things move in one direction, and therefore you have, like, you know, the simple pendulum. And well, here, let's say the Noether's principle, in a way, we can understand it in the way we described, like I have the Poisson bracket of a function with itself, it's going to be 0, okay? But you can also understand this, and that's the way that maybe it makes more sense from a physical point of view to understand this, okay? Is that you may want to think of this as a conserved quantity, okay? And you may think that this conserved quantity gives rise to some symmetries of your physical system, okay? And what's interesting, and that's an interesting point of the course, is that we are going to relate this to the existence of a group action on these manifolds. And this is going to be great. This is still not going to be present in these first slides, but I will explain you this in the next video. But so at the end of the day, we're going to see a group action, okay? And what's going to be very interesting is that in general, if you just have one first integral, there's almost no constraint on what this group may look like, okay? But if you are assuming that your system is integrable, then there are constraints of how your manifold, how your group, your Lie group looks like. And that's a key point indeed in the proof of the action angle coordinates. If we assume that if you are assuming that you have a compact fiber, then this group has to be a torus, okay? And if you assume that the action is, in a way, you assume that your manifold is complete, this means that the flow exists for all time, then you could have some cylinders, in which case the group behind it would also be a cylinder, okay? That's very interesting. So there are some groups behind. If I don't assume complete integrability, then the group can be much more difficult. Indeed, some of you are going to do presentations next week, which are going to be concerning these ideas of symmetries. I'm really looking forward to your point of view on this subject. Okay, so that's the, let's say that's the physical idea behind this, because Noether didn't prove this, let's say, in the language we are proving this. She didn't have this language by that time. That's the difference, okay? So in order to prove Noether's principle, okay, it was not as easy as it was for us. Okay, so remember a little bit, let's back up and let me recall the motivation for us to do symplectic geometry these days is that, well, the existence of symmetries of a differential equations, as I have just explained, allows the reduction of degrees of freedom. Okay, and the example that I'm taking here is the first example I took when I started this chapter, which is Hamilton's equations. Okay, here you have Hamilton. This is a picture of Hamilton. I could have put a picture of Noether. Maybe I should do that because tomorrow, as you know, is May 12th, is the day of human mathematics. So I should have added a picture of Noether. Okay, never mind. These are Hamilton's equations. Okay, I think that you can follow what I'm marking on the slides because this is recorded by Zoom and it's very effective. And remember that this is something that I have already explained, that Hamilton's equations correspond to the equations of the flow of the Hamiltonian defined by this equation, taking as the form, okay, the Darboux form, okay? So this construction can be done on manifolds of even dimension, generalizing the cotangent model. This was our motivation. Now let's look at the integrable system. What is an integrable system? This is a definition. This definition, you also have it in the notes, attention, you have it towards the end of the notes. And as I will explain in one of my emails, and not all the chapter on Poisson geometry is going to enter in the final exam. Okay, so I want to make sure to find the definition, because the definition is towards the end, but I'm not going to have you deal with vector fields concerning Poisson structure. So this is going to a little bit relax the contents towards the final exam. Okay, but this is exactly the definition. An integral system, sorry, it's given by n generically functionally independent functions on your symplectic manifold. Okay, so I need to have n generically functionally independent. What does this expression mean? N generically functionally independent, it means in practice that if you take f, you cannot take f squared. How do you explain this in a language in which you can understand? Well, the best way to do this is to take the differentials of the f, to wedge them, okay, and then to impose that this doesn't vanish on a dense set. That's the definition of generically functionally independent functions. That if you take the differential of the functions and you wedge them, okay, the set of points in which this vanishes has zero measure. All right. This is equivalent to the functions being functionally independent, generic. Okay, and I need to impose the conditions that they Poisson commute. Well, the Poisson bracket is given as the Poisson bracket on the whiteboard before. So it's just the symplectic form applied to the Hamiltonian vector fields of Fi and Fj, excuse me, in this particular order. Now, what is the theorem of Arnold-Liouville? Well, this is known in the literature as theorem of Arnold-Liouville, but I discovered later on when I was postdoc in Toulouse that indeed Henri Mineur, who was an astronomer, had already discovered partially this theorem, which you may find like a complete proof in the book of Arnold, okay? But you can also find the key expression of the action functions in a paper by Henri Mineur. So I'm going to call this theorem Liouville-Mineur-Arnold theorem. I'm not the only one. Quite a lot of people do this. So the theorem is the following. Under compactness hypothesis of what? I need to assume that the fiber, so that the fiber associated to this F, so F minus 1 of C, is compact. Then the integrable system is given by the Hamiltonian action of a torus, Tn. That's very interesting. That's a way to present the action angle coordinates. So what does it mean, Hamiltonian action of the torus? It means that certain vector fields, indeed what is called the fundamental vector fields of the action, this is something I'm going to recall in the next video, are Hamiltonian vector fields, okay? And that the symplectic form can be written in this way, in this particular way. So what's interesting about this, that here we have some coordinates that are the p's are the actions and the thetas are the angles, okay? So in this theorem, what's interesting about this, it tells me two things. First, it tells me that the topology of an integrable system of the fibers defined by F associated to F is extremely easy to understand. I have a fibration by tori. And secondly, it's telling me that the symplectic geometry in the neighborhood of this torus is extremely simple. There is only one local model. If I have another symplectic form, I can always find these coordinates in the neighborhood of a torus because they are semi-local, okay? This works in the neighborhood of a torus, okay? I can find action and angle coordinates such that omega can be written in this way. So omega has a kind of Darboux type expression, so I only have one local model, okay? But that's more than Darboux, but I have one local model for both the symplectic form and the fibration, because F in this system is going to look as the p's, as the actions in these new coordinates. I may consider this integrable system defined by the p's, and omega looks like this. That's the action angle theorem, coordinates theorem by Arnold-Liouville theorem, or Liouville-Mineur-Arnold theorem. Let me explain you what, okay, so that's a nice picture. So that's the first thing. That's the picture of the Liouville torus, which I can think of as a vibration. So this first torus is F1, Fn equals to constant. And the second one is F1, Fn equals to another constant. So I can imagine this as a vibration of a torus over a base. So semi-locally, the manifold I'm thinking of is Tn times a disk, where the disk is formed by the values of what we often call the moment map, which is the image, okay, of this integrable system. So I take F1, I take the value F2, and I look at the value and the set of values here in a neighborhood of a torus lies on a disk. Okay, so my manifold in a neighborhood of the torus is a product of a torus times a disk. Okay, and I can describe this manifold in coordinates. These coordinates are more than local. They are not global. They are coordinates defined on this piece of manifold, which is the torus times a disk. All right. And the tori are defined by pi equal to constant. Okay. And the symplectic form is simple in the sense that it's a Darboux symplectic form. All right. So that's a nice picture of what I want to say. And this slide is the summary of Arnold-Liouville theorem. Okay, Arnold, Liouville-Mineur. So I said Liouville-Mineur-Arnold because I do this not in alphabetical order, I do this in chronological order. All right. So that's a picture of Henri Mineur. Henri Mineur, if you look at Wikipedia, has an important role in the resistance in France. And I think it's very interesting to follow the story of his life. But he was also an astronomer and mathematician, and in particular gave explicit formulas of these action coordinates. He said, look, use symplectic form in a neighborhood of the torus. This is something that I will convince you later, because this is a theorem. Indeed, a theorem which I could say is due to Weinstein. I'm going to link now here a video by my colleague Anton Alexeyev, where he proves that in a neighborhood of a Lagrangian submanifold, you can always write omega as the differential of alpha. That's a theorem that we attribute to I think it's attributed to Alan Weinstein. I think it's, the proof I know is from Alan Weinstein, but indeed it was also known in the realm of integrable system. It was also known to Arnold. Okay, and well, the idea is that you have a kind of Poincaré theorem, okay, because omega is a closed form, okay, and then omega is locally exact. The miracle occurs when your point is inside a Lagrangian leaf that is compact. Then it is known then that you can make the proof of the Poincaré theorem, which is based on an homotopy, okay, that you can adapt this homotopy with the symplectic form. That's what my colleague, Anton Alexeyev does in this video here, okay, that you prove that omega is the differential of alpha. So in particular, in a neighborhood of the torus, that's a theorem. Omega is the differential of alpha. Okay. In a neighborhood of a point, that's trivial, because this is just the Poincaré lemma. Okay. But that this is true in a neighborhood of a manifold, okay, you need to have something going on this manifold. In particular, you need omega to manage on this manifold. Okay. And then you can apply the proof of the Poincaré lemma with the homotopy to prove that omega is the differential of alpha. Okay. Then you take this alpha and you integrate over gamma I. What is gamma I? Well, gamma I is one of the cycles of the torus. Once you know that your manifold defined by pi equal to constant is a torus, then you can take generators of the cohomology, the gamma I's, the cohomology of the torus, and you have n of them, okay? Because you are on an n-dimensional torus. And then you take these cycles and then you integrate alpha. And this produces, you integrate a one form over a cycle, this produces for you a function. And this function indeed is one of these action coordinates. Okay, that's a way to prove this action angle coordinate. After this this video, I will sketch proof using group action. So this is an interesting point where the theory of chapter 3 group actions meets the theory of chapter 4 symplectic geometry. Okay, examples. I'm going to talk about the harmonic oscillator. And I take one harmonic oscillator. Well, the harmonic oscillator, I can think of a spring. Okay, so this happens in dimension 2. But now I can try to couple two harmonic oscillator. Okay, two of them. This would then happen in dimension 4. And this example is going to sound familiar to some of you because this was the way I explained one of the questions in the questionnaire last week. In one of the questions was about the harmonic oscillator, and where there I was giving you two functions, and I was asking you to prove that these two functions Poisson commute, that the bracket is 0. All right. Some of you found, oh, I don't know what is the coupled harmonic oscillator. Well, you don't need to know. You just needed to compute, because I was giving you the symplectic form. I was giving you the function, so it was a way to ask you, well, compute the bracket. But I was justifying, look, you are computing the bracket, but look, this is the harmonic oscillator. So it's nice. It's the coupled harmonic oscillator. So here the configuration space is formed by x1 and x2, okay? And the phase space is the cotangent bundle of R2, where you have the symplectic form, which is the Wu symplectic form, okay? And the total energy of your system, okay? Of course, in the questionnaire, you didn't need to justify this. You just got given the energy. But if you have to find the energy yourself, then you need to remember that the energy is the sum of kinetic and potential energy. Okay, so you compute kinetic and potential energy. How do you compute potential energy? Well, because you remember Newton's second law. So you know the force is a mass times acceleration. Okay, and then you compute from there. Okay, the interesting thing about this equation is that if you put h equal to constant, this equation happens in dimension 4. This is a 3-sphere. In particular, a 3-sphere has a lot of symmetries because you can rotate this 3-sphere sphere. So that's the reason why the angular momentum, which is given by this function, you have, because of this rotation symmetry of the sphere, the angular momentum is a good candidate to Poisson commute with H because of this symmetry. This is the way to argue this. I'm not going to ask you in the exam to argue these things because this is in the realm of physics, but I just want to justify, let's say in a physical way, with intuition, why this is a good choice of first integral. And then it's just a computation to check that the bracket is 0. You just need, remember, the bracket coincides with the Hamiltonian vector field applied to H, and it's very simple because the Hamiltonian vector field in dimension 4 has this expression, okay? And now you apply it to H, and you get a 0. It's just applying this vector field to this function. So it's just a simple computation, and this is an example, therefore, of integrable system. Other example is the spherical pendulum, which you can see in the video here that Joachim explained the other day. And then you also have two first integrals that are that you can understand them from a physical point. Okay, more sophisticated problems, and that's well, I'm putting here on the last slide. This will not, in a way, I will not ask this by no means in the exam, of course, in the sense that here I put an example that, well, it's non-integrable, okay? Because one of the non-integrable examples is the movement of 3 planets on the sky, okay? Well, the movement of 3 planets on the sky is not the way to say it. I have 3 planets, and of course, these planets are attracted to each other 2 by 2, Okay, and you may think that if I look at the movement of one of the planets, I have to take into account this attraction to the two planets and the fact that this planet, that yourself as planet, are attracting the two planets. So that's what is classically known as the three-body problem, which is known to be non-integrable. Okay. Then I may consider easier situations of the three-body problem, like the restricted three-body problem, okay, which is also non-integrable, but sometimes with some constraints, you can find integrals. And of course, this belongs to the realm. I mean, finding these integrals is hard. Interesting thing that happens with this restricted three-body problem that has been very recently discovered. I say very recently, 2016. This is 4 years ago. This sounds recent if I compare to Poisson, Jacobi, and all these things, and all these big guys. Okay. I look at the restricted three-body problem. Okay. And here, well, the Hamiltonian you work with also has a physical interpretation, and it has this equation where the potential, takes into account the mass of the system. In the restricted three-body problem, I assume that the bodies move in a plane, okay? And I assume further that one of the bodies has zero measure, or almost zero measure, has zero mass or negligible mass, as we would use, negligible mass. This is the situation of a spacecraft compared to the Earth or the Moon. You can think that the mass is negligible, okay? So this would be a model where you assume that this move in a plane. So that's a very strong restriction, if you want. But sometimes you can restrict to this situation. So it makes sense to study this problem. This is called the restricted three-body problem. This is the Hamiltonian of your system. And then what's very interesting is that what has become very standard in the literature is to use this last slide for the people who freak out. This is just an invitation for research. This will not be asked in the exam. Okay. So in the sense that I will not consider, I could consider maybe this Hamiltonian, but not what I'm going to say now. That in the literature, usually people use what is called McGehee coordinates. And while people were working with these coordinates in a symplectic sense, and magic occurs. If you complete the symplectic form, this is no longer a symplectic form when x equals 0. Why? Because it goes to infinity, okay? But this is a good Poisson structure. So you may deal with this problem from a Poisson perspective. And that's something we realized 2016 with the help of Amadeo Del Sam, the professor of the other master course on Hamiltonian dynamics. So here you see how two master courses have something in common, and you can see that interesting research, I shouldn't say interesting research because it's the research that I do, but okay, yeah, I can say it, can be done with very basic language. Okay, so that's the end of this short video. I hope that you have enjoyed it. And you can ask me any kind of questions about this last problem. I will be very happy to answer. Okay, see you in the next video. Now I'm going to try to stop this.